We can also have circular apertures, or you could think of them as slits, but in a circle. And these also cause diffraction patterns, as you can see in this picture. So we want to know just what the this phenomena, how we can actually see this, and how we can actually resolve uh, whether we have two of these together or not. Uh, we don't know whether there could be two apertures here or just one. So we're going to look at how we can determine when we have that. And so resolution is the ability to distinguish uh, distinct apertures. So we say that if it's got good resolution, we can tell how many apertures or the what's going on in the picture or the view. Now, because we're talking about small apertures, then we assume that theta is approximately equal to sine of theta. We've used this approximation before. And our previous analysis was for rectangular slits. So to convert to circular, we use the conversion of, um, well, we'll derive that. And well, we won't derive that, we'll just get it here. So we know that sine of theta is equal to lambda divided by our distance of the aperture rectangular. And it turns out that our distance rectangular is approximately the circle distance, or the diameter circle, divided by 1.22. So if we make sine of theta equal to theta, put d rectangle in for our function here, we find that theta is going to equal 1.22 times lambda over d circle. That's our diameter of our circle aperture. Now, how do we resolve whether we can actually distinguish two uh, circle apertures or not? Well, we have Riley's criteria. And that tells us that the minimum distance to resolve two points. Let me make another page here. So I'm running out of room. 2 points is when the center is at the first or center of one point, is at the first minimum of the other. And we can see this here in this diagram where we have 2 points that are close together. And you can see how the center of this one and the center of the other are on the, if I can draw it here, on the minimums of the one next to it. And you can resolve this. You can actually see 2 specific dots, but if these were closer, you would not be able to resolve those 2. So how can we use this to our benefit? Well, let's say I'm designing a telescope. So here's my telescope, and I'm going to look at 2 stars that are far away. And if I think of this, I mean, we're talking light years, right? Very far distance. And in this case, if I take a look at a circle at that long distance, this little curve is going to look almost like a straight line. But I can use this idea of theta and say, well, if theta is this angle here that makes these 2 stars appear, and I'm not drawing stars very well, but then, and I know the distance r, then this distance, although it's a bit of a curve, I can use this approximation that s equals r times theta. And if I solve for theta, I get s over r is equal to theta. But that's just also equal to 1.22 times lambda over my diameter of a circle aperture. So if I'm designing a telescope and I want to be able to resolve these 2 stars, then I need to have this as my circular aperture of the telescope. So this is the approximation that we have to use, is using arc length. If we try to do this with triangles and do similar triangles, it's very difficult to do that. But a fast approximation, and it's close enough for, we're talking light years away. If we're off by a couple of 100,000 miles, it's not really going to matter. Then I can come up with this approximation using Riley's criteria, and I can find the aperture of a telescope that I need to be able to resolve stars at a great distance.